Alright, welcome to lesson 3. This is a pretty big lesson. Today we're going to talk about the definite integral and interpret the definite integral as the net area under a curve. Let's get started. So to begin with, let's take a look at this problem here. A particle starts at the origin and begins traveling along the x-axis. The velocity of the particle over the first 10 seconds is graphed below. In the interest of time, what you want to do is quickly sketch out this graph so that you can work with it on your own sheet of paper. Don't worry about copying down problems A through E. Just answer them on your sheet of paper using your graph as an aid, and then go ahead and press play and we'll take a look at them together. So the first few are very easy. We've done these many times. We know that the particle is moving to the right for the first 6 seconds because the velocity is positive, as we can see here. So to find the total distance that it's traveled, I just need to find the area between the velocity curve and the x-axis, or in this case, the axis that measures time. In doing so, I end up with an area of 9, which means that my particle is now at the point x equals 9. So I've drawn that on my diagram, traveled to the right. When t equals 6, I'm now at the point x equals 9. But at that point, there's a switch. All of a sudden, the velocity becomes negative. And so that means that my particle is switching direction. Instead of moving to the right, it's now moving to the left. And I've illustrated that here in the diagram. The question that we really want to answer, though, is exactly how many units to the left is the particle going to travel over these last 4 seconds. Let's apply the same strategy that we did for finding the total number of units that travel to the right. Let's find the area between the x-axis, the time axis, and the velocity curve, and try and interpret that in a way that will allow us to figure out how many units it moved to the left. The first, perhaps troublesome spot that we run into is that we're used to using the value of the velocity curve to determine one of the dimensions of the shapes. And in this case, the value of the velocity curve that we're using is -4. And we're not used to dealing with negative area. But we need to remember that our goal is to multiply a time interval by a velocity to find a distance. And so from that perspective, multiplying a positive time interval by a negative velocity makes perfect sense. And that will help us to understand what the area that is quote-unquote negative represents. So let's go ahead and find the area here. 2 times -4, and since it's a triangle, I then divide by 2, which will give me -4. And here I have 2 times -4, which is -8. How do I interpret this? Well, this would be traveling 4 units in the negative direction, or to the left. This would be traveling 8 units in the negative direction, or to the left, which makes sense since my velocity is negative. In total, I'll travel -4 plus -8, or -12 units, meaning I've traveled 12 units to the left. This makes the question of where the particle is after 10 seconds quite easy to answer. Thinking about it in terms of our answers part B and part D, traveling 9 units to the right and then 12 units to the left will leave our particle 3 units to the left of where it started, or at x equals -3. Thinking about it as the sum of all the areas, if I simply add them all together with the negative representing a movement to the left, I'll end up accounting for the direction thanks to the sign here. So 2 plus 6 plus 1 plus -4 plus -8 is -3. We now know how to handle functions that are both above and below the x-axis. As we saw here, it was vital that we maintained the same method we have previously, where we are using the value of the curve to determine one of the dimensions so that we're preserving the negative sign. And then we can simply sum up all of the areas, and I use that word liberally here, to find the net area. And we're going to continue to do that. As you see, when we define the definite integral here in a second, we will have these negatives preserved. So before we get to the definite integral, we need to discuss Riemann sums in a little bit more detail. I'm going to try and go through this pretty quickly. If you want a little more of an in-depth look, go to page 281 and read through it. What you've noticed by now is that when we've been approximating the area under a curve, we've been adding these areas together. And when you're adding a bunch of things together that are formed in the same way as these areas are, it's convenient to have a way to write that addition or that summation in a much more succinct way, instead of something plus something plus something for a very long time. And the way we do that is with sigma notation. This is the Greek letter sigma. It corresponds to the letter S, and that's why we use it to represent a sum. The k equals 1 here, this refers to the index. It doesn't matter what the variable k is. It could be anything we choose. It just tells us where to start. So in our expression, there will be this variable k, and we'll start, in this case, when k equals 1. And the number at the top of the sigma tells us where to finish. So real quickly, we'll start when k equals 1, which means we'll substitute 1 in for k into our expression and evaluate the expression. So that will give me a sub 1. Then I go back, and the index increases now to 2, and we'll apply that value of k. That gives me a sub 2, so I add it to what I had before. And I keep going all the way up until I get to the last, or to the number at the top, a sub n, as I have here. Okay, so this will allow us to represent Riemann sums in a much more efficient way. So now we're ready to discuss Riemann sums in a little more detail. You don't need to copy all of this down. It's more important that you listen carefully, pause, maybe rewind if something doesn't make sense. So the Riemann sum actually isn't a Riemann sum because it has to do with area. It's called a Riemann sum because of the way that the approximation is constructed. So let's discuss how it's constructed. Regardless of the function being positive or negative, as long as it's continuous on an interval from a to b, the Riemann sum approximation, what it tells you to do is to split up your interval into subintervals. This is called partitioning, or to partition the interval. And in fact, the Riemann sum, it doesn't tell you that the subintervals have to be the same length. We happen to do that because it's more convenient and makes the mathematics a lot easier. But all it says is to break it up in any way that you want, as I've done right here. After you've partitioned your interval from a to b, you're going to go into each subinterval, and you're going to pick any point you want within the interval. We've been picking specific points, either the left endpoint, the midpoint, or the right endpoint. Don't worry about trapezoidal Riemann sums for now. And then with that point that we choose, we're going to evaluate the function at that point. And we're going to use that value of the function as an approximation for the function on that entire subinterval. I've shown that here, picking an arbitrary point in my first subinterval, evaluating the function at that particular point, and then using the value of the function at that point as an approximation for that entire subinterval. Then what I'm going to do is I'm going to multiply the length of the interval by the value of the function that I'm using as my approximation. Notice, because the value of the function could be positive, well, positive up here, negative as we have here, or it could be 0, this product that I'm taking, this multiplication, can be negative, as it will be here, it can be positive, it can also be 0. So when we visualize it as a rectangle, and we think about this product as representing the area of a rectangle, that's where we have to remember that in this situation, we could have a negative, quote-unquote, negative area, okay? As we saw in the discovery problem, this is necessary. So here's the first rectangle. Now, the Riemann sum approximation says to do this for each of the subintervals and then add those products together. First subinterval, multiply the length of the subinterval by the value of the function at that randomly chosen point. Then I do the same for this subinterval, and then I add those two together. Do the same and continue on. I'm going to fast forward to what this would look like if I've done that for each subinterval. All right, so here's the completed version. Notice that I've denoted all of the arbitrary points that I've chosen in each interval as C, and so we have C sub 1 to denote the first interval, C sub 2 to denote the point in the second interval, all the way up to the very last interval, which we'll call the nth interval, since we can go up to as many intervals as we want, and this will be C sub n. I chose a random one in the middle, and I'll call that C sub k, just to represent any point in any of the intervals. So the point then that I'm using to approximate the value of my function over that interval is going to be the point given by the x value of C sub k, whatever that C value was that I chose, and then the y value is just the value of the function at that point, f of C sub k. Also remember that I stated for a Riemann sum, it actually doesn't matter how big each subinterval is. They can all be different lengths, but it's more helpful if we let each subinterval be the same length. So we call that length delta x, and the way we find that is by taking the total length of the interval from a to b and dividing it by n, in other words, the number of intervals that we want, so that we get n intervals of the same length. And we'll call that delta x. All right, now we're ready to write out our sum. We're going to be taking the product of the length of each interval, which for each interval is going to be delta x, and we're going to multiply that by the value of the function that we've chosen for that particular interval. So for the first interval, our product will be f of c sub 1 times delta x. And we're adding to it the product from the second interval, which will be f of c sub 2 times delta x. And we're going to continue doing this all the way up until the very last interval. So let's go ahead and write those all out. I'm going to skip ahead to c sub k, some random point along the way, and then close out with c sub n. And so there is our completed sum. Notice I've skipped a few along the way so that I can get all the way to the end. A couple things to keep in mind, of course, are that while we can think of each of these as being an area, these products, some of them can have negative value, like the first two, for example, in this situation, since the value of the function that we're using to approximate the curve on that interval can be negative. Delta x, however, always going to be positive. Now we can see how using sigma notation is going to be really helpful in writing out this sum. Instead of writing them all out, all we're doing is changing the value of the input for our function along the way. First we're choosing c sub 1, c sub 2, c sub 3, and so we're really adding things that are very similar over and over and over again. So instead of writing it all out, we can use sigma notation. I'm going to be going from 1 all the way up to n, and the things that I'm going to be cycling through are these c sub 1, 2, 3, all the way up to n. So I'm going to have in my expression f of c sub k, so that when k changes, c sub k changes, and we'll cycle through all of the points that I want to hit. And I'm going to have to multiply by delta x. So there is our summation. Notice that if we were to follow the rule of sigma notation, we will end up with this same expansion that we wrote to begin with. And this is the definition of a Riemann sum approximation for a continuous function f over the interval from a to b. If you want to dive more deeply into the definition of a Riemann sum approximation, head to page 281 and 282 in your textbook. At this point, we want to take a look at the definition for a Riemann sum approximation and think to ourselves, what can we do to make our approximation better? What would we have to change? What would we have to manipulate? That's the first question. Once you've decided what it is you need to do to make your approximation better, you want to then think about what is a concept we know that we can use in order to make that happen. So spend a couple of minutes thinking about that. You might go back to some of the work you've done with our approximations before and think about what you had to do to make your approximations better. To make our Riemann sum approximations more precise, we want to increase the value of n. And the reason that we want to make more subintervals is that the more subintervals we have, the smaller each subinterval will be. And the smaller each subinterval is, the better our approximation that we're using within each subinterval will approximate the true value of the curve over that subinterval. You should be able to see this visually, that the smaller I make each of these rectangles, meaning the more rectangles I have, the better job it will do of approximating the true area between the curve and the x-axis. Just to get a solid visual of this, let's take a look at one from the book. Even though this particular partition of the subinterval doesn't make each subinterval the same size, it's still very clear that when I increase the number of subintervals, the rectangles are doing a better job of approximating the area between the curve and the x-axis over the entirety of the curve. So now that we know how to make our approximations more precise, can we make them exact? What would we need to do in order for the area underneath our rectangles and between the rectangles and the x-axis to be the exact area between the curve and the x-axis? Think about it for a second. What would need to be true? What you'll realize is that in order for our approximation to be exact, we need every interval to be so small that the approximation that we get from the random point we choose within our interval is going to be the exact value of the true function on that interval. In other words, we need the intervals to be so small that it only consists of one point, so that that's the only point we can choose. And of course, when we choose it, the approximation that we get by plugging it into our function is, of course, the only value of the function on that interval. So how many intervals will we need? We'll need an interval for every point from A to B. How many points are there from A to B? That just boils down to how many real numbers are there from A to B. There are infinitely many. So we need infinitely many subintervals in order for our approximation to become exact. By now, of course, we know that we're never going to be able to do something infinitely many times. So is there a concept that we have which will allow us to approach a value and to think about the value of an expression as we approach something, even if we can't actually substitute that value in? We saw this when we computed instantaneous rate of change. We couldn't substitute in the value that we wanted into our expression of average rate of change, so we had to look at the limit. And here, since we can't make infinitely many subintervals, we'll have to use the limit to see what will happen to our sum as n approaches infinity. So we take the limit as n approaches infinity of our sum approximation, which just looks like this. The limit as n approaches infinity of the sum from 1 to n of f evaluated at c sub k times delta x. The value of this limit is known as the definite integral of the function f of x on the interval from a to b. With that being said, let's write out this definition. The definite integral of a continuous function on the closed interval from a to b. So let f be continuous on this closed interval from a to b, and let this closed interval be partitioned into n subintervals of equal length, delta x, which we get by taking the length of the interval from a to b and dividing by n. Then the definite integral of f over the closed interval from a to b is given by the value of this limit, the limit as n approaches infinity, of the sum from k equals 1 to n of f evaluated at c sub k times delta x, where each of these c sub k's are chosen arbitrarily in each interval. That's a lot. But at this point, you have a few questions. One of the main questions you should have is, how do I even find this limit? Do I even know this limit exists? And that's a big question, which at some point you'll prove the answer to if you take enough classes in college. But for now, we're going to take a look at the theorem that you would eventually prove, which is that all continuous functions are integrable. Meaning, if a function f is continuous on a closed interval from a to b, then its definite integral over the closed interval from a to b exists. Meaning, this limit will exist and we can find the value of it. Now that we know that is possible, our goal is going to be to actually find strategies for finding the value of the definite integral. We already know how valuable it can be in looking at the couple of application problems that we have, particularly dealing with area under velocity curves and its relation to total distance and whatnot. Before we go on to that, we want to take a look at the notation that's used here. This is fairly laborious and cumbersome, but a little bit of thought will lead us to an easy simplification of this. So first, consider this. Delta y over delta x, which we know of as the average rate of change between 2 points, or the slope of a line between 2 points. And we remember this from our work with derivatives, where we looked at the average rate of change and tried to use that to find the instantaneous rate of change. And the way that we did that was we took the limit as our change in the x values approached 0. And what happened when we took the limit as delta x approaches 0? Well, we ended up with the derivative, or the instantaneous rate of change, which we denoted as dy dx. And these are called differentials, and they represent the infinitesimally small change in x, and accordingly the correspondent infinitesimally small change in y. And we see here that this is happening in this limit. We're taking the limit as n approaches infinity, and since n determines the size of delta x, when n becomes infinitely large, that means delta x is becoming infinitely small. So what we're thinking about is that within the limit, delta x is acting just like the differential in x, or the infinitesimally small change in x, which makes perfect sense when we consider what happens to the rest of our sum when we take the limit as the number of subintervals approaches infinity. When that happens, we're actually going to be evaluating our function at a point in infinitely many subintervals, so at infinitely many points. In other words, at every single point from A to B. So we'll be summing this product infinitely many times smoothly over our curve, not jumping from rectangle to rectangle. And so we have a new type of notation that represents a sum that happens continuously over every point from A to B. We use an elongated Roman S to represent this continuous sum. It looks something like this. We want to denote that our continuous sum is going from A to B, and that at every point along the way, we're going to be computing the value of the product. Since we're doing this at every point from A to B, we don't need to use these C sub k's anymore. We can just use f of x because we're using every x value from A to B. And we're going to multiply it by the differential of x. And so this is integral notation. And the way that I would read this is the integral from A to B of f of x dx. And thinking about it, I am imagining a continuous sum of these products, these infinitely small products, at every point from A to B. So now that we've completed our definition, we have a little bit of new notation, and here are the names for each piece of the notation. So write this down, learn it. It's on page 284 if you want to go take a look at what the book has to say about it. One last thing that I'm going to mention is that this variable, the variable of integration, is just the name of the variable that we use for our horizontal axis. And so as we've seen before, we don't always have to use x. Sometimes we'll be thinking about time, so we might use t. We might use u. So for example, we could have the integral from a to b of f of t dt, or integral from a to b of f of u du. We'll pick the variable based on what the circumstance is, what the situation is, whatever makes sense in that particular setting. All right, now at this point, to familiarize yourself with using this notation and understanding what it means, head to page 284 and work through example number 1. After you've done that, go ahead and press play, and we will begin our process for evaluating definite integrals. So little did you know, we've actually been evaluating definite integrals already when we are finding the area between a curve and the x-axis. We've found the exact area by taking advantage of geometric shapes like rectangles and triangles that we know how to find the area of. And we've approximated, when we can't do that, using rectangular approximations and trapezoidal Riemann sum approximations. So this leads us to an interpretation for how to evaluate the integral from a to b of f of x dx. The way that we do it is we calculate the area between the curve and the x-axis that is above the x-axis, and we subtract from that the area between the curve and the x-axis that lies below the x-axis. And if you go back to the discovery problem, this should make sense, because when we're calculating those Riemann sums, any area that's below the x-axis ends up being negative because the value of the function is negative. And anything that's above, any area that's above, is positive because the value of the function is positive. So we end up subtracting away all of the areas that fall below the x-axis. And so this is a way for us to compute or evaluate this integral. Notice there are a couple ways that we can find this area as I just described. We can approximate these areas using Riemann sums, or we can find the exact value, if that's possible, by taking advantage of geometric shapes that are formed by the function that we can find the exact value of. So let's go ahead and apply this idea to evaluate some integrals. All right, let's start by evaluating the integral from -2 to 2 of the square root of 4 minus x squared dx. Try this first on your own, and then we'll take a look at it together. All right, I want to evaluate this integral, and so I'm going to take advantage of the fact that I can compute the area above and the area below and subtract the two in order to evaluate this integral, or this continuous sum. So first I'm going to have to graph the function. Be careful that you only graph on the interval that you're considering, which is from -2 to 2, so you don't end up including extra area that you don't need. Then I'm going to compute the area that's above the x-axis, between the curve and the x-axis that's above, and between the curve and the x-axis that's below, and subtract. So here's the graph of my function. You may notice that this is a semicircle with radius 2, but if not, that's okay. You can graph it in your calculator. Hopefully, as you become more familiar, you will begin to notice. And we can see here that all of the area is between the x-axis and the curve and lies above the x-axis. So we're just going to have to compute this piece, and we won't have to subtract anything away. There'll be none of those continuous sums that end up with negative values because my function has a negative value. It's always positive. And since it's a semicircle, we can compute the exact area using the area for a circle and dividing by 2. And there you have it. The area of a circle divided by 2. The radius is 2. So I have 4 pi divided by 2, which is 2 pi. And therefore, the integral from -2 to 2 of square root of 4 minus x squared dx is equal to 2 pi. Let's try another one. All right. Try this one again on your own, and then go ahead and press play, and we'll take a look at the solution together. All right, same strategy as before. I'm going to take a look at the graph of cosine x on this interval, and then I'm going to use a trapezoidal Riemann sum with 3 equal subintervals to approximate that area between the curve and the x-axis, being careful that what's below is subtracted away from what's above. And that will be my approximation for this integral. All right, here's the graph. Make sure that you are labeling with your radian measure, because that's how you're going to break up your subintervals. You have an interval from 0 to 3 pi over 2, and so when you divide that by 3, each interval length, subinterval length, will be pi over 2. So you go from 0 to pi over 2, then pi over 2 to pi, where cosine is at -1, and then from pi to 3 pi over 2, where it's at 0 again. All right, now we're going to just go ahead and compute our trapezoidal approximation, and that will be our final approximation for the definite integral. When I construct these trapezoids, one of the side lengths is going to be 0, and so that leaves me with just triangles, which is nice, and makes the approximation quite simple. Notice, of course, that this is above the x-axis and these are below, and so the value of cosine that I get will be negative, which will cause me to subtract these away from the area that is above the x-axis. I can factor out a pi over 4 from both and then compute cosine at each of these and evaluate. And there you have it. I end up with negative pi over 4, which you can clearly check makes sense because I have more area beneath the x-axis than above. In fact, I have one triangle above and then two of the exact same triangles below, so I will end up with negative pi over 4. All right, at this point, go ahead and complete the homework for Unit 7.03.